Picture this. You're brewing a fresh pot of coffee. The aroma is swirling in the air. Or maybe you're watching a drop of ink slowly disperse in water. Have you ever stopped to think about the force behind these everyday occurrences?
It's not magic, but a fundamental principle of the universe at play, a concept called entropy.
Okay, entropy. I've heard the word before, but I'll admit it's always seemed a bit mysterious.
It's a concept often shrouded in misconception. Entropy isn't about disorder or chaos, as some might suggest. Instead, it's a measure of how spread out energy is within a system, a way to quantify the number of possible microscopic arrangements consistent with its overall state.
So it's not about how messy a system is, but rather how many different ways its components can be arranged at a microscopic level.
Precisely. Think of a simple system like a box filled with gas molecules. Those molecules are constantly in motion, colliding with each other in the walls of the box. Each specific arrangement of those molecules at a given moment represents a microstate.
So a microstate is like a snapshot of the exact positions and velocities of all the gas molecules in that box.
Yes, and there are countless possible microstates for a given system. The more ways those molecules can be arranged while still maintaining the same overall energy and volume, the higher the entropy.
I'm starting to see how this connects to the coffee aroma spreading. If the coffee molecules are initially concentrated in the cup, there are fewer possible arrangements for them. But as they spread out into the room, they have more freedom to move, increasing the number of possible microstates.
Exactly. And this drive toward a higher number of microstates, towards a greater spreading of energy, is at the heart of entropy.
But how does this spreading actually happen at the molecular level? It seems like those coffee molecules would just randomly bounce around with no clear direction.
And you're right, the movement of individual particles is random. We call this process diffusion, the natural movement of particles from regions of higher concentration to regions of lower concentration. Imagine dropping a dye into water. Each dye molecule is jostled around randomly by collisions with water molecules.
So even though each individual molecule's movement is unpredictable, the overall effect is a gradual spreading of the dye throughout the water.
Right. We can model this movement using what's called a random walk. Imagine a particle taking a series of steps, each step's direction chosen randomly, over time. Even though there's no preferred direction for each step, the particle tends to move away from its starting point.
Okay, I can see how that would lead to the overall spreading we see in diffusion. But you mentioned that entropy is connected to the overall state of a system. How do scientists define those overall states?
We call them macrostates. A macrostate describes the system's observable properties, like temperature, pressure, or, in the case of our coffee, the overall concentration of those aroma molecules in the room.
So the macrostate is like a general description of the system, while the microstates are the specific arrangements of particles that fit that description.
Exactly. And here's the crucial link to entropy. A single macrostate can correspond to many different microstates. Think about arranging books on a shelf. You could have a macrostate of books arranged alphabetically.
But within that macrostate, there are still many different ways to arrange the books, different microstates, depending on the order of authors within each letter.
Precisely. And the more possible microstates that correspond to a given macrostate, the higher the entropy of that macrostate.
So a system with more possible microstates for a given macrostate has a higher entropy. It's like the system has more freedom to be in different configurations while still maintaining the same overall properties.
That's a great way to put it. And this brings us to one of the most fundamental laws of physics, the second law of thermodynamics.
The second law of thermodynamics. That sounds intimidating. Does this law have anything to do with why my desk always seems to get messier, no matter how much I try to tidy it up?
It's not directly about your desk, but the principle applies. The second law of thermodynamics states that the entropy of an isolated system can never decrease over time. It can stay the same or increase, but it can never go down.
So you're saying there's a natural tendency for systems to move towards states of higher entropy, towards greater spreading of energy, and a higher number of possible microstates.
Exactly. Think about what happens when you drop an ice cube into a glass of water. The ice cube melts, its highly ordered, low-entropy structure giving way to the more disordered, higher-entropy state of liquid water.
But why can't we just put the water molecules back into the ice cube tray and reverse the process? Why is there this one-way direction for entropy?
That's where things get really interesting. The second law of thermodynamics doesn't tell us why entropy increases, just that it must. But one way to think about it is that there are simply far more ways for a system to be in a high-entropy state than a low-entropy one.
So it's like rolling dice. There are many more combinations that add up to 7 than combinations that add up to 2. A high entropy state is simply more probable.
That's a good analogy, and this probabilistic nature of entropy has profound implications, especially when we consider the universe as a whole. If entropy is always increasing, then the universe is constantly evolving towards states of greater entropy.
So does that mean the universe is destined to become a homogeneous soup of particles, where everything is evenly spread out and there's no more potential for change? A kind of heat death, as I've heard it called.
The heat death is one possible scenario, but the ultimate fate of the universe is still a topic of much debate among physicists. Some speculate about the possibility of multiple universes with different entropy levels, or even mechanisms that could lead to a decrease in entropy under certain conditions.
Okay, so the jury's still out on the ultimate cosmic implications. But you mentioned earlier that entropy applies to more than just simple systems like gases. Does it play a role in more complex systems too?
Absolutely. Take biological systems, for example. Living organisms are highly ordered, seemingly defying the tendency towards entropy, but they only maintain this order by constantly taking in energy and releasing waste products, thereby increasing the entropy of their surroundings.
So life itself is a delicate dance with entropy, maintaining order within while contributing to disorder outside.
That's a poetic way to put it. And this interplay between order and entropy extends to many other complex systems: the flow of information in a computer network, the evolution of cities, even the spread of ideas in a society. All of these processes can be understood through the lens of entropy.
It's fascinating to think that a concept that started with observing something as simple as coffee aroma spreading can have such profound implications for understanding the universe and all its complexities. But there's one thing I'm still struggling with. How does entropy relate to our experience of time?
That's a deep question that has puzzled scientists and philosophers for centuries. You see, entropy is often linked to what's called the arrow of time. The reason why time seems to flow in one direction from past to future.
Wait, so you're saying entropy might explain why we can't travel back in time? This is getting mind-blowing.
It is a mind-boggling concept indeed. One way to think about it is this: if you could film a process that increases entropy, like an ice cube melting, and then play the film in reverse, it would look completely unnatural.
Because we never see melted ice spontaneously reform into a perfect cube. It goes against our intuitive sense of how time flows.
Exactly. And this asymmetry in time, this arrow pointing from past to future, could be fundamentally linked to the fact that entropy always increases in the universe.
Okay, I need a minute to wrap my head around this.
Yeah.
So you're saying we can't unscramble an egg or unspill milk because those actions would decrease entropy, which is forbidden by the second law of thermodynamics.
Yeah,
And this is somehow connected to the very nature of time.
you've got it. It's like the universe has a one-way street sign when it comes to entropy, and that sign might be what gives us our sense of time moving forward. Now, while we've been talking a lot about how entropy is connected to the macro-scale behavior of systems, it's important to remember that the concept is rooted in the statistical mechanics of microstates.
Right. We were talking about how entropy relates to the number of possible microstates corresponding to a particular macrostate.
Exactly. And that statistical interpretation of entropy has implications that go beyond what we've discussed so far. For example, it can help us understand why some processes are irreversible, even though the laws of physics are time-symmetric.
Hold on, I thought you just said entropy explains why time moves forward. Now you're saying the laws of physics don't distinguish between past and future.
It's one of the great mysteries of physics. At the microscopic level, the equations that govern the motion of particles are the same whether time runs forward or backward.
So if we could reverse the motion of every particle in the universe, would time run backward?
That's the question, isn't it? And it gets to the heart of what makes entropy so fascinating. It's intertwined with our very perception of time.
So we've gone from the scent of coffee to the very nature of time itself. This idea of entropy, the increasing spread of energy, and the drive towards a higher number of microstates. It's a lot to process.
It is a fundamental concept that touches upon some of the deepest questions in physics and cosmology. And as we've seen, it challenges our intuitive notions of order and disorder, of reversibility and irreversibility.
You mentioned earlier that entropy is connected to the arrow of time, this idea that time flows in one direction. How does that play out on a cosmic scale? What does it mean for the eventual fate of the universe?
Well, if entropy continues to increase, as the second law of thermodynamics suggests, the universe could eventually reach a state of maximum entropy. This is the heat death scenario we touched upon earlier, where all energy is uniformly distributed, and there are no longer any temperature differences to drive work or change.
So no more stars burning, no more galaxies forming, just a cold, dark void where nothing much happens. That's a rather bleak picture.
It's one possibility, But remember, we're talking about processes that unfold over incredibly vast timescales. And there are other factors to consider, like the role of gravity and the ongoing expansion of the universe.
So the universe's fate might be more complex than just reaching a static state of maximum
Well,
entropy.
absolutely. Some physicists believe that even in a universe at maximum entropy, there could still be fluctuations at the quantum level, perhaps leading to the emergence of new structures or even new universes.
So there's a glimmer of hope for avoiding this cosmic heat death.
Perhaps. There's still much we don't know about the interplay between entropy gravity and the fundamental nature of space-time. And as our understanding of these concepts evolves, our picture of the universe's ultimate fate might change as well.
It's humbling to realize how much we still have to learn. But this journey through the concept of entropy has been eye-opening. We started with everyday observations, like the spreading of coffee aroma, and ended up contemplating the very fabric of the universe.
And that's the beauty of science. It allows us to connect the mundane to the profound, to see the universe in a grain of sand.
Indeed, it makes you wonder what other seemingly simple phenomena might hold the keys to unlocking even deeper mysteries of the cosmos.
That's a question worth pondering. And perhaps as we continue to explore the universe and its laws, we'll find that the most profound insights lie hidden in plain sight, waiting to be discovered in the everyday wonders that surround us.
Well, on that note, I think we'll leave our listeners with this final thought. The next time you see a drop of ink swirling in water, or smell the aroma of freshly brewed coffee, remember that you're witnessing the fundamental principle of entropy at play, a force that shapes not just our everyday experiences, but the very evolution of the universe itself.